All right, so recording's going on, so that's good. So I want to just recap a little bit about where we are. This is the last section in in chapter three, kinematics of deformation, and we were talking about kinematic rates. So in the major portion of this chapter, we have talked about the deformation tensor. That's where everything starts usually. Deformation tensor F is equal to the gradient of the spatial coordinate with respect to the material coordinate, also written as partial x over partial material x. We have been seeing that this is a static measure, meaning it doesn't involve time dependence. Time or finite rate dependence. And we have been also looking at kinematic rates in section 3.6, which deals with finite rates. So to recap, we have seen what are called the material derivative and the spatial derivative. So this is partial x or partial g over partial t at a given x, and this is dg over dt for a given particle. So this is what we saw a couple of lectures ago, where g is any quantity which has a spatial representation and a particle or material representation. What we also know is that you can go from g to g tilde by using x equal to phi of x comma t, and you can go the other way, g tilde to g, by using the fact that x equals phi inverse of x comma t. So once you have derived the representation for a quantity either in spatial form or material form, you can go back and forth as necessary. We saw all this 2 lectures back, and we also derived for velocity and acceleration. We calculated the velocity in material frame, or the particle velocity is x dot. The acceleration in material or particle frame is x double dot. So once you have x dot and x double dot calculated at a given, so this is basically partial x over partial t at a given x, and this is second derivative of x with respect to time for the same x or particle. So if you are thinking about what does fixed x mean or fixed particle mean, it represents the it represents all the positions occupied by the atoms which we designate as a particle. So think of the droplet example, or where you have a droplet that is initially in a spherical shape in one location, but over time, as the droplet becomes divided into smaller droplets, all those small droplets are also part of the same particle. The positions occupied by them are also considered part of the particle's position. So given x could mean a large area or volume in space, because that particle can be divided, subdivided, deformed, change shape, and so on. Again, once you have derived the expression for velocity or acceleration in a particular frame of reference, you can always go back and forth by transformation. We did an example and a quiz last lecture on this, and you can write, if you take the velocity in the spatial form, you can calculate the acceleration AI, or the component of acceleration AI is partial Vi over partial T plus Lij times Vj. This Lij is the component of the velocity gradient tensor. Velocity gradient tensor, which we can write L is gradient of V, which is partial Vj over partial xi. I'm sorry, I got that backward. Partial Vi over partial xj. And clearly, as you can see, Lij is a spatial tensor because it has two indices, both of which are derived from the spatial coordinate system. The dyads, both the dyads are spatial vectors. Famously, the deformation tensor is a mixed tensor. You know that. Any questions so far? Am I being audible? Is everybody okay? Some feedback will be nice. Say just you can just speak up because I'm not seeing the screen. That is the Teams screen. So anybody, if you can unmute and talk, that will be useful.
Everything's clear so far?
Okay, good.
Everything
Thank you.
understand?
Thank you. So then in section 3.6.2, so whatever I described so far comes under um, section 3.6.1, and under 3.6.2 we saw rate of change of deformation measures. So we are used to the deformation tensor F, and we calculated F dot is L dot F. That is Fij dot is Lij times Fjj. We also saw that if you take dx, the element differential element in spatial frame, the rate of change of dx, if you calculate this, this is equal to, I mean, instead of doing it in vector form, we will do this we did this in index form. So if you take dxi and the derivative of that, that would be f dot, sorry, that would be Lij times dxj. Lij times dxj. So the deformation tensor F, the rate of deformation tensor F dot, and the velocity gradient L. These three quantities are basically the quantities that will keep repeating as we calculate different measures of deformation from basic observations. So let me repeat that because so basic observations or measurements come in two flavors. Either you can do spatially focused. That is, you are trying to put a sensor at every point in space and trying to record a quantity at that point at a given time or as a function of time. This is at this the example I keep giving about. If you stick a hot wire anemometer or a velocity meter at a given point in a flow and just record the velocity at that point, that would be a spatially focused observation. You can also look at material focused or particle focused. Those would be G tilde, which is focused on a particle. Wherever that particle is at that instant, you track that object, which may or may not deform. The simplest example we came up with is tracking a baseball as it goes across the park. You are tracking the position of the particle. Of course, the baseball happens to be a rigid body, so it doesn't change shape. So x is just a point. The uppercase x is just a point. But if x can deform, it can be a droplet or a piece of metal that is changing shape, etc. Then it would be a material-based or material-focused observation. In either case, or in both cases, we extract quantities like x or material X, which together determine somebody is having their mic unmuted. Can you please mute yourself? Okay. Maybe I need to do this for you. Chandrasekhar, can you please mute yourself?
Yes, sir.
Yeah, there's some background coming from your end. Thank you. So the spatial as well as the material coordinates that we calculate, they lead us to the deformation tensor. You know that. And deformation tensor depends on both coordinates because it's a mixed tensor. And then you can calculate F dot, the rate of deformation. You can also calculate L, which is velocity gradient, also known as strain rate tensor. So these three quantities are the core. With these quantities, we'll be able to calculate everything else that appears in this unit, in this segment of rates. Okay, so maybe this is something you need to keep in mind. So then we also saw rate of deformation, which is basically saying rate of change of distance, not position but distance. Okay, the scalar. So we started with what is ds squared, which is dxi, and we wanted to get the rate of that. I won't go through the entire derivation again, which we spent about significant part of a lecture. So this is equal to 2 Lij dxi dxj. So notice that Lij appears here. Either F is usually reserved for static measurements or static measures. We saw the strain tensor. We saw the RU decomposition, VR decomposition. There F appears. But in the case of rates, it'll always be L or F dot. And of course, F dot is related through L to F itself. So this L assumes a very important role in the description of deformation rates. Okay. So you have Lij, and Lij is decomposed as the sum of a deformation part and a vorticity part. So this D is called rate of deformation tensor, and this W is called the vorticity tensor. Excuse me. Are we okay so far? I mean, I'm just recapping, but I think this is necessary. Otherwise, today's lecture will look a little unsettled. So this rate of deformation tensor D is calculated as L plus L transpose divided by 2. You can also write Dij, Lij plus Lji divided by 2. Obviously, D is symmetric. So you would get ds squared dot is equal to 2 times Dij dxi dxj. Because the antisymmetric part will not contribute to this, we went through this derivation. And the other tensor W is defined as L minus L transpose divided by 2, which will be Wij equals Lij minus Lji divided by 2, which will make this a antisymmetric tensor. So the physical interpretation is D deals with deformation or length changes. W deals with orientation changes. So if something is rotating, it will have a non-zero vorticity. If it is purely rotating, it will have a non-zero vorticity, but a zero deformation tensor or the symmetric part. Okay, this is up to where we came last lecture, or maybe we did a little bit more, but effectively in terms of topics, this is what we have covered so far. Any questions before we move on?
Sorry,
I think he disconnected.
yeah, maybe.
Do we need to do anything to get him back?
He's traveling, I think so.
Hello. Hey, sorry. I disconnected. I got disconnected from my iPad, but just give me one more moment. I'll join so that I can do my screen share. Okay. Sorry. Come on. Hello. So I'm able to join, and I'm going to do something here. I hope you can hear me. So
Yes,
I'm going
sir.
to save this file and open it on my computer here so that I can just type up the notes instead of writing it, which is still okay. Okay, I think I'm finally back. Somebody confirm? Can you hear me?
Yes, sir. We can hear you.
Okay,
Yes, sir.
okay, thank you. Okay, good. Okay, all right. So you're seeing this. Let me continue. So we talked about rate of change of stretch, rate of change of stretch. Okay, so that would be ds dot ds dot, which is equal to dij dxi dxj divided by ds. Make this font size a little bit bigger. So I didn't want to continue the rest of the derivation and talk about logarithmic rate of stretch. I think that's a little bit advanced concept. We just want to understand if you have a length ds, what is the rate of change of length and how would you calculate that? Or if you want to calculate the stretch, which we define stretch ratio, which we define as alpha dot, this is equal to the rate of change of stretch divided by the original length ds. And this is given as, this is essentially going to be dij dxi dxj divided by ds squared. So why do we need to know this rate of change of stretch? Because usually we try to simplify problems down to 1 or 2 dimensions. If you have a complex 3-dimensional problem, rarely we will analyze the entire 3-dimensional nature. We try to make assumptions such that it's better analyzed as a quasi 1D problem, so that if you can describe the mechanics of in just 1 dimension, you can get a lot of insights and design ideas from that. So that's why understanding how to calculate this ds dot based uh, on the spatial vectors is something that we consider useful. Okay. Other than that, the logarithmic stretch and relating that to the Lij, as well as defining a quantity called m, those things are left to you, but I'll just continue or stop here. Okay. All right. I'm sorry about the technical glitch we had. And then the rate of deformation tensor. So sorry, the next quantity we are sort of interested. Copy this right here. Rate of change of volume. So we want to write. So I want you to recall something from maybe few lectures ago. What is the relation between the volume element dV, or it has a special symbol here. Do we have that symbol here? Okay, we'll just go with dV. dV in the spatial frame, which you may consider as dV equal to dx1, dx2, dx3. Okay, and the volume element in the material or particle frame, we write dV naught, which you can write as dx1, dx2, dx3. What is the relation between these two? We did this discussion maybe a few lectures ago. How do what factor or what quantity relates the two volume elements? Can you recall?
Is it just the deformation tensor?
It is not just the deformation tensor. dV is equal to J times dV naught, where J is equal to the determinant of the deformation tensor. J is a scalar because deformation tensor obviously is a scalar. So we try to write, we first calculate the deformation tensor from the actual deformation and then compute a scalar J which relates the change in volume. So remember, just to help you recall, I understand some of this can be a little off-putting. We did discussions on what is the relation between we discussed relations between dx vector, that is the change in position vector, and dx, the material vector, or the change in position of the particle, that is again related through what? This is a really basic idea. What are dx and d material x related through? You had the answer, Mark.
The deformation tensor?
They are related through the deformation tensor, through the deformation tensor, F. And if you are wondering how, exams next week, so we would just write this. dxi is Fij dxj, which you can write in vector form as dx vector. How will you write this in vector form? Dx vector equal to F. I'm going to say it. F. Dot You guys are kidding with me, right? You know the answer, you just won't say it because it's a Teams class and right? Dx equals F dot D material X. We also saw what is the relation between dA or n cap times dA n cap times dA and n cap or n uppercase, which is the normal vector of the area element in material coordinates. N cap and dA naught are related through the deformation tensor, which I won't write again. I'll just write through F and J, which is determinant of F or the so-called Jacobian. And this relation, actually, we discussed this. It's given in an earlier section. You just turn the pages back to section 3.4.3. You can find this relation. So I'll put the hint here, section 3.4.3. So that would be n cap dA equal to J times J is a scalar. Okay, so J is a scalar. You can multiply the scalar with F inverse transpose dot n dot n dA naught. This is the vector form or the vector form. In index form, this would be Ni. What is dA? dA is a scalar or a vector or a tensor. Did the connection drop again?
I think a scalar.
Scalar. dA is a scalar. It's an area. It's a number. It's the area of some surface, right? We give the area orientation to make it into a vector. That's the n cap. So this is dA equal to J being a scalar, and we need F inverse transpose. So F inverse transpose would be raised to the -1. Usually we write F I, I being spatial, J being material. But since this is this is a transpose, this would be I multiplied by N, and N is a material vector. So you would have Ni dA naught. So we saw relation between vector length elements, relation between area elements. So if you know either the area vector in material coordinate or the spatial coordinate, you can go back and forth. If you know the left side, you can get the right side. If you know the right side, you can get the left side. Are we together so far? Is this coming back to you?
Yep, makes sense.
Right. I mean, I'm repeating this after 3 or 4 lectures, because these things are never something that we just get it instantly, at least not for me. So it takes a little bit of repetition on my side to make this sync with you. Okay, so forgive me if I'm repeating myself. And then d v and d v naught are related through J, the determinant of the deformation tensor, and dV is J times dV naught. So this is just static measures. What is you have a length element in one frame of reference, what happens to it in the other frame of reference? The deformation tensor helps you calculate that. So in the first equation here, if you know the dx material and the deformation tensor, you can obviously calculate the dx spatial. Or if you know dx spatial and the deformation tensor, you can calculate the dx material. Or if you know both spatial x and material x and their derivatives, you can compute f from that. In the second equation, once you know f and you can calculate the determinant of f, you can then use this relation to calculate what happens to an element. Suppose you have a square face in a surface which is like a square pointed along the x-axis in the material frame. You subject that to a deformation described by f tensor. What will happen to that area? Will that area become a rhombus? Will it change orientation? Will it still be will it still be pointing along the x direction? You can figure that out. If you know f, you need to compute f inverse transpose dot n multiplied by dA naught. That will be the value of the area, and the orientation is given by this part here. So this exactly will give you n cap. So you can even think of this as Ni, oops, Ni is given as Fii inverse Ni, whereas dA is given as J times dA naught. So that when you multiply the two, you get the change in the scalar area as well as change in the vector, position vector. So this is a little bit of recap about how the length, area, and volume elements are related to each other in both the frames of reference. What we are asking here is the rate of change of volume. We want to calculate, I'll write dV, and then I have to put a dot on top of that. So I have to calculate dV dot. That's the goal here. And coming back, dV dot would be yeah. So we want to start with J, which is determinant of F, determinant of F. Okay, we want to consider what is J dot. Question is, what is J dot? Others, are we okay? Am I making sense to you? Can you please give me some feedback? Samyak, is it okay? NC?
Okay, sir.
Yeah, it's
Yes,
okay.
It's fine. Yeah.
it's fine. Moteza?
Yeah.
I mean, forgive me if I repeat myself. I have to do this. These things take time to sink in. So that's why I'm repeating myself from 3 or 4 lectures back. Okay. All right. So the time is also 6:51. Does anybody have any objection if we go on until 7:25?
No
No
objection.
problem, sir.
No problem. Okay. Thanks. I really appreciate that. Okay. All right. J dot we want to calculate. So this is going to be equal to uh, we want to write this is a derivation I want to go through because it will teach you some things along the way. Okay, so we want to write this is determinant of f dot. The way I've written here might be a little confusing and not consistent with the book. So I'll try to use this here. All right, so you have determinant of f, and I need the dot of this. Oops. Okay, just 1 second. I need to get this right. Otherwise, it's easy to write this, but not type this. First, let's get the dot. And within the dot, let's get the dash. All right, got it. And then determinant of f. So this is the determinant of f, which is a scalar. Remember that. And the time derivative of that scalar. So that is what we are trying to compute here. Okay. So this would be obtained as partial derivative. Okay, or if I expand this, this would be the partial derivative of determinant of f with respect to time. That's what dot means, right? So this we are going to write is the partial derivative of the determinant of f, okay, determinant of f with respect to f itself, oops, with respect to f, okay, respect to f. And then we want to do a double inner product, that is a double summation, with f. The end result has to be a scalar, and it shouldn't just be f, it should be f dot, or f with respect to, oops, f with respect to time, which we will write quickly as f dot. All right, before we go further, I would like you to take a good look at this part here, and tell me if you're okay with this manipulation.
Yes, sir.
Yes, okay. All I've done is apply chain rule. Take a time derivative, express that as the derivative with respect to f, and then multiply it with the rate of change of f. But since f is a tensor, you're going to get a tensor. Determinant of f with respect to a tensor, determinant of f is a scalar. But if you are trying to do this with respect to a tensor, you will end up again with a second order tensor. So the double inner product is to ensure that we eventually get a scalar. So then we'll continue the derivation. J dot is equal to what is this quantity here? This quantity is nothing but f dot. I mean, that's what dot is, right? It's just a shorthand for time derivative. So I'm going to write, I need to first get a dot, and within the dot, I need to put a double dash to denote the tensor. And then what is this quantity here? Determinant of f with respect to f. So the book basically writes this is equal to J times f inverse transpose. And how would we convince ourselves that that is all right, that is correct? Or how does the book get that expression for J inverse transpose dot f? How do we go from here? This expression is equal to J inverse transpose. How do we prove that? In the first unit, that is the unit on tensors, there was an identity which we proved in the homework. I don't know how many of you would remember that. I'm just trying to find that identity for you. Go to, if you have your book in front of you, page 21. Page 21. Go to page 21, take a look. We have the expression or the proof for the partial derivative of determinant of A, where A is some second order tensor. It's not deformation or anything. It's just a tensor. With respect to the tensor itself, A, this is equal to, or this is given as A inverse transpose times determinant of A. I can almost replace A with F and we'll get this part taken care of. Anybody remembers this identity or working on it in the homework? You can say no, it's okay. I'm not going to judge you.
No, I don't remember.
Okay, so if you go back to homework 1, this is one of the identities which we proved. And we started with the expression for determinant, and then we wanted to get the derivative of a determinant with respect to an arbitrary component of the tensor A, and you will end up with this expression. So I mean, I would ask you to go back and look at your homework 1. It's sitting right there. So all I'm doing is counting on us to have already proved this, and using that result, determinant of A or determinant of F, we have given it a special symbol J, and J is a scalar, so you can multiply it later or before, multiplied by F inverse transpose, which is same as A inverse transpose. So this is J dot. What is here? F, you know F because the deformation is known. If that is known, if it has a time dependence, you can get F dot. How do you get F dot? How can you get F dot? We just, at the start of this lecture, I mentioned what is the relation between F and F dot. So F dot, the rate of change of deformation, is related to F as L, the velocity gradient tensor, L dot F. L dot F. Rate of deformation tensor F. F dot can be expressed in terms of L and F. Okay, so this will give you, this is equal to J. You still have F inverse transpose. Okay, and then you are doing a double inner product. So you have to do sum over all the indices so that eventually you will left only with no index, and that should be done with L dot F. Again, take a look. Tell me if you agree with me. So this expression, rate of deformation tensor, if it looks a little new to you, it shouldn't, because this is what we discussed last lecture, and you can find this in page 95. So what I've done is to get J dot in terms of J and F, which is inverse transpose, I mean, F, which is a fundamental quantity, and L, which is like a velocity gradient, which is basically the rate of change of velocity spatially. Okay. What can I do next? What do you look at F inverse transpose, you also look at F. So there is some room for simplification, would you think? I will take that silence as a yes. Okay. So we are here. We have come up to this point. Okay. So we want to simplify this expression and see if that can be done a little bit less painful. So the book suggests using an identity. Now, if you ask me, would you be able to do this identity switch? Not 9 out of 10 times, but if I practiced, I could. So what the book basically says is it gives us the steps to get to a final result. So I'm in the same boat with you. I may not be able to do this derivation if you take the book away from me, but the point is to get a final result which I can interpret meaningfully. So I have to persist until I get the final result, which is what I also ask you to do. You have to see the final result, and that is a simplification, or that is a elegant result which will be useful even if you can't recall the steps of the intermediate derivation. That makes sense? I'm being straight with you. What is important and what is a detail? The derivation is a detail, granted, but the final result is important. So you have to go through the derivation to get there. Okay. I hope you would agree with me. Yes, no. So I'm writing A, double inner product, B, C, B dot C is equal to B transpose B transpose dot A, and then that inner product or double inner product with C. All right. Question. What is the rank of B dot C where B is a second order tensor and C is also a second order tensor? What is the rank of B dot C where you do the inner product once over one index? Let's say vector B followed by dot product vector C. What is the resultant quantity? No one would talk.
Is that first order?
So B dot C is a scalar, zeroth order, right? B dot C is a scalar. Okay. What is BC? That is B. I'm not putting any dot in between, just BC. What is BC?
Scalar.
All right. B
MECH.
dot C is
BC.
BICI. BC, what is BC?
Is it second order?
The second order tensor, BICJ, and then you have to include the basis vectors EI, EJ. EI, there is the cap, yep. EI, EJ. This is a second order tensor. Okay. If you take a second order tensor like B dot C, let's just take B. Take a second order tensor and then you dot it with a vector, which is a first order tensor. What do you get? What's the resulting quantity? This would be Bij. Let's say you would have EIEJ. EIEJ. Okay. And then you have C, which you have to dot. We'll write CK EK. EK. What is this? This is Bij, CK, EI, and delta JK. I'm going to save us one step and write this is CJ. What is this quantity? Is a vector. Come on, guys. Are you not speaking because this is an online class, or you just not seeing this? NC, is this acceptable
Yeah.
to you?
Yeah,
Samyak?
unfortunately, I have a connection problem and it's getting interrupted with something. It just like I can't hear you completely sometimes.
Okay, yeah, that's unfortunate. I'm also on the same boat today. But is this, would you agree with me that this is a first order tensor or a vector?
Yeah.
Samyak, you've been awfully quiet today.
Yes, I can see. Yeah.
Right. So this is a vector. Now, if you then ask what is B dot C, trying to come to build up to what we need here now. What is B dot C? Bij. You need to put EIEJ, right?
Yeah.
EIEJ, and then you have to dot this. Oops, you have to dot this with tensor C, which we'll write C KL, and then we have to put EK EL. All right. A dot product eliminates two indices. It reduces two indices to just one, right? You get a delta function. So you get Bij, C, KL, and then you have EJ, EI, and
EIEL,
EL. Sorry. Come again. EI.
EIEL,
Okay. Just one second. You're right. It's going to be EL. EIEL. But for those who don't want to be kind of like thrown the answer at them, I'm going to put the delta JK in between the EA and EL, which is totally okay because delta JK is a scalar. I can put it wherever I want. So delta JK. So then wherever K appears, I have to set it to J. So this is BIJ, CJL,
JL,
and then I have
EIGL.
EIEL. Okay, EIEL. So I can write, I'll just use a dummy index, call this K, and then I'll just put EJ. It's a dummy index, right? So I can just change the name. And this is a what quantity? This is
Second
a
order time.
second order tensor. Okay, one more test or one more quantity that I want you to consider. P double inner product C. So where the dot appears, I'm going to put double dot or colon. What is this quantity? Bij. I have to put EIEJ, right? EIEJ. And then I'll put that colon, and then I'll put C, KL,
Yeah.
and then I'll put EKEL. EKEL. So don't like be confused about this colon. You can just think of it as two dot products evaluated one after the other. So this is Bij, C, KL. Those are scalars. You have a sequence. You have EIEJ, and then they are dotted with EKEL. So dot the two inner ones first. So you'll have EI. You'll have EI. You have EI, and then you have to do EJ dot EK.
Yeah.
Okay, I'll put those within a parenthesis. Okay, and you may be wondering where is the other dot? I'll put dot
EL.
EL. So I'll have delta JK and delta IL. So I'm going to have Bij C J I. What is this quantity? It's a scalar, right?
Yes, sir.
So this is a little recap of our unit 1 tensors, and we now need to understand B dot C is again a tensor. A tensor double dot another tensor is going to be a scalar. So the right hand side, left hand side is a scalar. So here also you have a tensor double dot or double inner product with another tensor, which will give you scalar and scalar. So that's good. Consistently, that's good. The proof of this identity can be proved by expanding in index notation, which I won't do right now, but it's not impossible for you to do this. Okay, so if we use this identity, we are going to end up with J identity tensor I. So this here basically, if you treat A to be F inverse transpose, L to be B, and F to be C, you have to take you have to take B transpose dot A. What is A? A is F inverse transpose, and then double inner product with C, which is F. So yes. So this is equal to J times identity tensor double inner product the velocity gradient L. I'm deliberately skipping over that because we have only about 5 minutes, but it's definitely not impossible for you to literally substitute this identity and get this final result from here. Okay. So the derivation so far has led us to J multiplied by a scalar which is I double dot or double inner product with the velocity gradient. Okay. All right. So then I had to spend a few minutes here to recap this, but I hope that was beneficial. So this I double dot L, they further simplify this. This is what is L? What is L? L is gradient of velocity, grad V, where V is a vector. I dot V. And this I dot V can be proven to be equal to divergence of V. That sounds simple enough for us to actually try. So what is I? What is okay? Let's evaluate this. How will you evaluate this I dot P? Just like you did in the previous slide, we did B double dot C. How will you evaluate I dot P? What is I?
Identity vector.
Identity tensor. An
Tensor.
identity tensor is basically delta Ij multiplied by EIEJ. EIEJ. And then I have to do uh, double product or double inner product with what is velocity gradient. How would you express that?
VK, EK.
Velocity gradient is if you write L KL, this is partial derivative of V K with respect to XL. Okay, so this will be double product multiplied by EKEL. Okay, so this is velocity gradient. Page again 95. All right, so how do you simplify this? First, you have to do the dot product with J and K. So wherever K appears, you can make it J. And then later you would do I and L. Wherever L appears, you can make it equal to I. So this is going to be simply partial of Vj
VK
over
by XI.
Xi. This is divergence of V. That's straightforward. Basically, sorry, you also have a delta Ij. So you have to make I and J equal to each other. I mean, first you set K equals J, then you set L equals I, and finally you have to set I equals J because you have identity tensor, which will get you this partial Vi over partial Xi. which is nothing but divergence of velocity. So that's a neat simplification there to have. Okay. So this gives us J dot. Oops. So this basically gives us is equal to J times divergence of V. So J dot is related to J just through the divergence of velocity. All right, I'm going to ask you a question. What is the relation between F dot and F? I said this 2 or 3 times in just today's lecture. What's the relationship between F dot and F?
F dot is equals to
F dot equals to this one
uh,
right here. F dot equals to L dot F.
L dot F.
L dot F. Okay. The reason I'm asking or saying that is you have a deformation. Okay. That is F. That's described by F. And then if it has a time dependence, that is, I need to make this connection here. So go back to the basics. What is X? Or what is the deformation mapping? X is equal to phi of X. This is the deformation mapping. Okay. So this is deformation mapping. When you include a time dependence, when you write the same thing with the time dependence, it becomes what is called as
X comma T.
X comma T. This is, oops, X comma T is motion. Motion is basically, it includes time dependence. So this allows you to get F, right? I won't say how. At this point, we all know it's related to the material X and spatial X. And this allows you to get velocity,
L.
either in spatial or material frame. You can get velocity if you know the motion. You can get acceleration if you know the motion. If you know velocity, velocity gets you velocity gradient, L. Velocity gets you velocity gradient, L. So specifying the motion gets you deformation gradient, as well as velocity gradient. So what we are then getting here is this relation F dot connects the rate of change of deformation with the velocity gradient and F itself. We have now derived J dot is equal to J, which is related to the deformation gradient, and del dot V, which is related to the motion itself, which because it's related to the velocity. This describes the rate of change of volume at a given point in space. If the volume is changing, it can change only through one way. It has to a volume change over time is possible only if the divergence of velocity is non-zero. Number one. Number two, the quantity J dot or quantity J is always positive. Why? Because J connects a change in volume volume cannot be negative. You cannot shrink something or you cannot make it go away. It has to be either unchanging or it has to be changing or increasing, or it can be less than 1, but it cannot be less than 0. So J is always 1, which will mean J dot, yeah, I'm out of time here. J dot represents the volumetric strain rate. Okay. So I'm going to stop here because I'm 2 minutes over time already. But this practically wraps up this unit. I just have just one more topic called Reynolds transport theorem, which will take about maybe 20 minutes next lecture. But for the remaining 2.5 hours of the next lecture, we will go through example problems, including the homework problems, and help us prepare for the exam on Tuesday. Okay. So with that, I'm going to wrap up today's lecture. Stop the recording. Oops, I apologize for the technical snags. And also I thank you for accommodating